Okay, everyone, we're going to get started now. So just want to welcome you to this session and thank you so much for tuning in. I know there's a lot of webinar options out there right now, and I want to thank you for taking the time to join us here today. We're going to have a great session in irrigation. And this is part of the Getting into the Weeds, Dialing in Irrigation seminar series. This is the third part of the series, and today we're going to be talking about operating and managing a drip irrigation system. So just a few housekeeping items first, just to let you know that all participants have their audio and video turned off during this webinar, so you don't need to search around for that mute button. We do encourage you to ask questions though, so please use the question and answer feature. It's at the bottom of your screen, and my colleague here, Francisco, will be watching the question and answer, and we'll be jumping in, asking Ted some of those questions. And if preferred, you can use the chat function as well. That can be viewed by all of the participants. But again, we kind of encourage that Q&A feature so that we can keep track of all those questions. And first, I just want to give you an overview of Perennia, a very brief overview. So our vision is to be a recognized world leader in Nova Scotia, producing innovative, environmentally responsible, safe food of impeccable quality. And our mission is to support growth, transformation, and economic development in Nova Scotia's agriculture, seafood, and food and beverage sectors. So we have a number of different service areas, and this webinar is being brought to you by the Agricultural Service Area, but we also want to let you know we have areas like the Quality and Food Safety team, the Product Development team, there's Lab Services, and also Fisheries are one of our newer additions. So if you're interested in any of those service areas, please reach out to Francisco or I, and we can connect you with the right people. We might be able to support you in some different areas that normally you didn't know were available. So we'd be happy to help you with that. And so this session with our guest speaker today is actually part 2 of a series looking at drip irrigation. So I just want to give you a really brief overview of the last session. You didn't necessarily have to watch it to attend this session, but just want to let you know what we did talk about in the previous one. So our guest speaker talked about the annual water requirement and the peak flow rates, and those are used to assess the flow that's needed to operate the trickle irrigation. He also reviewed emitter placement and run times to regulate the discharge rate, looking at watering the crop uniformly. And he also went over the lateral pipe sizes and zone sizes with several crop examples. He also left you with some homework questions, so hopefully you had a chance to look at those. I did send those homework questions again through email. And, if you had a chance to look at those, our guest speaker is going to be giving the answers at the start of this session. And so I did send that email yesterday around noon to all of the registrants for this webinar. So if you want to have a quick check in your email, you'll be able to pull up those homework questions. We also included chapters from the BC Trickle Irrigation Manual, and those can be used for your reference, after this session. There's also a link to watch the part 1 of our guest speaker's talk if you're interested after this session, diving into some more of the details with the design side of things. Because today's topic is operating and managing a drip irrigation system. And our guest speaker is Ted Gulik. And just to give you a background about Ted, he's worked for the BC Ministry of Agriculture for the last 35 years in irrigation and water management. So he has extensive knowledge in this area. He's got an international reputation for his leading edge work in this area. He literally wrote the book on irrigation. He wrote the BC Trickle Irrigation Manual that you've got some copies of, some of those chapters, and several other publications as well. He was the lead developer of one of the lead in the development of the agriculture water demand model and a water calculator. He's the recipient of several awards, like the International Irrigation Association presented him with an award, and he also received the Premier's Legacy Award. Currently, he's retired, but he is the president of the Partnership for Water Sustainability in BC. So we're very happy to have you here today, Ted, and I'm going to pass it over to you.
Thanks, Michelle. I will open up my PowerPoint here. On here. Can you see that?
Yes.
Okay, thank you. Okay, so what I'll do first is I'll go through the answers on the problem sets that I gave out the other day. I'll also cover these other topics: filtration, chemical treatment for a drip system, and scheduling a drip system. So we'll start with exercise number 1, which was on strawberries. And we assumed they were in Kentville. The plant spacing was 1.5 by 5 feet, rooting depth of 1/2 foot on a clay loam soil. And we were going to use a T-tape system with 90% uniformity. The layout of the field was 360 feet wide by 900 feet long, with a header line going across the top of the field, and then the lateral lines running down the length of the field, just one line from the header line all the way down. And there was, it says 0% slope here, but I think the actual problem said 1% slope. So calculating the area of the farm, it's 7.43 acres if you take 360 by 900, which is 3 hectares. I won't go over all these formulas. You can review the video to see how this is calculated, but you can calculate the water requirement by going into a website called Farm West. Tells us that the annual demand over the growing season is 211 millimeters. That's the climate moisture deficit. We multiply that by the 3 hectares, a conversion factor of 10, and our 90% efficiency. We come up with about 7,000 cubic meters for the farm. The peak flow rate that the farm would need would be 7.43 acres times 4.6 gallons per minute per acre, because that was the peak ET that we came up with. It could be higher. If it was 4.8 or 5, you would multiply the number by 5, and your flow rate for the farm would be higher. Now, a drip system can quite often get by with 30% less. It just means you're going to have more zones. So to calculate the plant water requirement, we start off with the soil storage. We had a 1/2 foot depth. We're in a clay loam soil that stores 2.5 inches per foot. We can only use about half of that. We come up with about a very low soil storage of 0.6. That soil storage factor is used, that soil water storage rather, is used in a table in the book called the soil water storage factor, which is based on both your climate, peak climate, and your soil storage. And in this case, our soil storage factor is 0.85, meaning that the soil storage can carry us through the next day or the following day if the ET should go a little higher than 4.6. That's really what it's trying to say, to keep the same level of soil moisture approximately the same in the rooting zone. Our plant area was 7.5 square feet. Crop coefficient factor is 0.75 for strawberries. If we put all those numbers into this formula, as you can see down here, I have to convert the 4.6 millimeters per day into inches per day to make it work in the formula, because everything is British terms, square feet, and so on. We come up with 0.54 gallons per plant per day. The drip system has to supply a bit more than that because we need to take into account leaching efficiencies, uniformity. Leaching in Nova Scotia, you guys get enough precip over the wintertime. We don't have to worry about that. So the factor is 1, but the efficiency of the drip system is 0.9. Emission uniformity we're desiring is 0.9. So that moves the total water requirement up to 0.66 gallons per plant per day. There are 585 plants per row here. And so with each plant taking 0.66, the demand for the row is 386 gallons per row per day. And it's important to calculate it that way so you can relate it to the product supplying the water. There's some obviously headlands around the field, so I'm calculating 68 rows in the field. I'm going to take T-tape TSX 500 5/8 inch diameter, which is in the back of the sprinkler manual. It can supply, it can go for 900 feet with a 90% uniformity, and it has a 16-inch outlet, which is sufficient for what we're talking about, and the flow rate is 0.17 gallons per minute per 100 feet of product. So the flow rate for one row would be 0.17 times, and I'm saying 880 feet because we're not quite going 900. You could go 900 feet because usually the pipe isn't laying really, really tight anyway. So 900 would maybe be a better number. Regardless, it's about 1.5 gallons per minute. It might be a little bit higher than if you go to 900, or 90 gallons per hour. So if we have a supply of 34 gallons per minute and we're supplying 1.5 gallons per minute per row, we can run 23 rows per zone. That's how you determine the zone size. Since we have 68 rows and we could run 23 of them at a time, it would take 3 zones here across the top, 3 automatic valves to run our system in total. So total number of zones is 3 zones. The operating time per zone, if you remember, the flow required for the entire row was 386 gallons per row per day. We're supplying 90 gallons per row per day. So the operating time that we're estimating at the peak time of the year for the strawberry in this location would be 4.3 hours per day per zone. Since we have 3 zones, 4.3 hours per day is 12.9 hours, about 13 hours. When you do this a lot, you get a lot of experience on this. And right away, when I see that number, I know I did my calculations right. Because strawberries, if I'm using the peak flow of 34 gallons per minute and 3 zones, it always comes in around the 12, 13, 14 hours. You shouldn't see 20 hours. You shouldn't see 8 hours. It'll come around that. So you can see that we have a lot of operating time left. So we could go to a lower flow rate. Let's say we only had maybe 25 gallons a minute, and we might have 5 zones or 6 zones. It would still be able to be done in 24 hours. And that's what I was alluding to before when I said drip systems can get by with a lower flow rate. It's good not to do that. It's good to take your peak flow rate, because over time, your drip system might clog up a little bit and you want extra time to run it. Or you might get into a situation where you got behind for some reason and you can catch up in a day by just running things longer. So the second exercise we had was blueberries. We were again using Kentville, and the reason I use Kentville is because we have a weather station in Kentville. If you go to farmwest.com, you can see the weather station there and get the data right off of it. We're still using the 4.6 millimeters per day. I should say I came up with higher numbers when I looked at different years and different times, up as high as around 5 millimeters per day. So that would increase the flow rate a bit. For our blueberries, the plant spacing is 6 by 10. The rooting depth is 2 feet on a clay loam soil. We're going to use 0.5 gallons per hour. I think that's 1 liter per hour. Point source pressure compensating emitters operating at around 15 psi. We're going to put 2 emitters per plant. The maximum pressure loss in the lateral that we're going to allow is 7.5 psi. You can go higher with pressure compensating emitters, but I wouldn't recommend that because you will get blowouts on your lateral line as possible. So you want to keep at an operating pressure in the 15 to 20, 22 pounds range. They can go higher, but this is a nice operating range. Our layout for blueberries was a field 500 feet wide by 700 feet long. And that area is 3.25 hectares. And so calculating the farm water requirement as we did before comes up with about 7,600 cubic meters. Our peak flow rate now is a little bit higher because we have a larger acreage. It's 37 gallons per minute. Our soil storage is a 2-foot rooting depth. We're still using clay loam, so 2.4 inches per foot. We can only use, effectively, the plant can only take out half of that. So we multiply that by half, brings us to 2.4 inches of soil storage. If we go back to that soil storage factor table with the climate data, The soil storage factor is a little bit lower than it was for strawberries because we have more storage of water in the soil. It's 0.75. The plant area is 60 square feet. The coefficient for blueberries is 0.8. Putting all of these into this formula, 0.623 is a conversion factor, 0.18 inches per day, the conversion, and all the other factors, we end up with 4 gallons per plant per day. The trickle system design requirement is going to be 4 gallons per plant per day. Leaching is still 1, but our efficiency and emission uniformity are still 0.9. That moves the value up to 5 gallons per plant per day. We don't have to calculate the runtime now using the row. You can, you'll come up with the same number, but since we're putting 2 emitters per plant, and they're a half a gallon per hour each, we're supplying 1 gallon per hour of water to the plant. Since the plant needs 5 gallons at the peak of the season, their operating time is 5 hours. 5 gallons divided by 1 gallon per hour. It's a pretty simple calculation. And that's usually what I do when we're talking about point source emitters on larger plants. If we're talking vegetables and strawberries, you have to go to the row method because you really don't have an emitter exactly per plant. And so that would end up in an error if you did it that way. We have 48 rows in the field. There's 112 plants per row. The emitters per row, there's 2 per plant, so that's 224 at half a gallon per hour each. The flow rate per row is therefore 112 gallons per hour or 1.87 gallons per minute. The maximum rows per zone is calculated by the 37 gallon per minute supply, which we calculated earlier, divided by 1.87. So we can run 19 rows at a time. And therefore that still divides into 3 zones. And we're running them at 5 hours per day each. So that's 15 hours per day. And that number again makes a lot of sense when you've done this a lot of times. It falls in the right ballpark. Now, we don't have to run 19 rows per zone because if we do that, we have 1 row with only 12 rows in it. We could divide this into 16 rows per zone and do 3 equal rows of 16 rows, and in which case the flow rate is 30 gallons per minute per zone, so less than 37. So now what about the drip line? For hard hose systems, we calculate the standard SDR factor, which is calculated by the emitter flow rate divided by the spacing. So half a gallon per hour every 3 feet. That value is 0.17. You keep that number and then you can go to these charts in the back of the book. I'll show you an example of a chart in a second. The lateral line friction loss must also include barb losses, and that's up to about 30% of the line loss. The emitter operating pressure is 15 psi, as we said. If we go to figure 8.4, which I'll show you in a second, it shows a friction loss of 15 feet, which is 5.4 psi, plus the 30% barb loss is equal to 7 psi, roughly, for a 700-foot lateral of 16 millimeter ID poly. So our total operating pressure at the beginning of the line should be around 22 psi. This is the chart I was telling you about. You would have to interpolate on this chart where the 0.17 value is going to be between these 2 lines in this case. I know the graphic is kind of bad, but if you go to the chart figure 8.4 in the back of the book, you'll see a clear chart. You go up on 700 feet to that point and across, and it gives you the friction loss of 15 feet. So that kind of is a summary of those 2 exercises. Before I move on, maybe Francisco, is there any questions at this point?
Yes, we have one question, and this question is related for wild blueberries. And it says, if you're using an aerometer to monitor soil moisture, what would you think the moisture should be kept at during bloom, mid-season, and at the last 2 weeks before harvest?
That is a good question, and I'm going to be covering that in detail in the next part, in the end of the presentation. So I'll wait to answer that one at that time.
Okay.
Okay. Okay. If there's no other questions, we'll move on to the part about operating and managing a drip system. So the first thing is about maintaining your system and making sure that it doesn't get clogged up. And so I'm going to talk about a filtration, algae control, and managing precipitates that could form. So what are the causes of emitter clogging? Well, it's going to be organic material in the water supply. You will have algae growth in the lines and emitters, and that's possible if you have some chemicals in there and it's exposed to the sun, you can get algae growth. You can have silts and clays in the water, mineral things in the water that can only really be taken out by filtration. And you can have precipitation of chemical in the emitter line. You'll see that this graphic, which is also in the book, sort of a graphic about trying to determine what the filtration capacity should be. You don't want to over filter your drip system because then you're taking out way more material than you need to. You're going to be cleaning your filters quite often. And so you really want to be in this ballpark where you're filtering out enough that these particles can't form a bridge. And we found that about 6 to 7 particles can form a bridge and eventually plug up an emitter orifice. This is something I haven't tested myself, but I read in the literature. So you need to have a filtration system that's fine enough to take out a particle of that size. So when we're talking about filtration, you really need to think about a number of things. Of course, what type of filter, and I'm going to go through that. You'll see here we have screen filters and sand filters. You have self-cleaning screen filters. You have disc filters, which is basically another screen filter. The filtration system you choose is going to depend on the volume of water you put through it, the water quality, the organic or inorganic material in the water, the type of irrigation system, which is obviously drip system here, any downstream filtration you may also have, and then of course the size of the filter. So there's a lot of things that go into selecting which filter. I can tell you that in BC, we do have quite a few sand filters, but more and more people are going to mesh filters or screen filters, and they put them in, not in series, but not sort of a bank of them. So they just keep adding a filter if they need more flow to go through them. And I'll be discussing that a little bit as well. So there's a guide to filter selection, and you don't have to follow this, but it kind of gives you an idea. If you have organic material greater than 10 milligrams per liter, which you see in the very bottom here, you should go to an automatic sand media filter. And in fact, I don't think anybody puts a sand media filter in unless it is automatic. So we really don't even use manual sand media filters if we're at this level. We always go to an automatic sand filter. But as you get into these better water quality, but you still have some problems, a manual screen filter works fine if you're at less than 5 milligrams per liter. A manual disc filter is a little bit better because it has a higher filter area. So they're easier to clean. I think they're better than just a screen filter by far. And then an automatic screen or disc filter if you're getting into higher levels of inorganics. So this is sort of the one that is really sort of taking off. People may put in 10 or 15 of this if they have a lot of flow. And there's still some sand filters going in as well. They have some advantages, and I'll be talking about both. So what mesh size should I be looking at in my screen filter? If you're using a drip emitter, you need to filter out 1/10 of the emitter orifice diameter. And if you're using a spray emitter, which I haven't talked too much about, you can go down to 7 times the emitter orifice diameter. So your orifice can sometimes be listed in inches, millimeters, or microns. This table gives you the value of each. And it tells you once you know what your orifice opening is for your filter, for your emitter, and your manufacturer would tell you that information, or they would tell you a recommended mesh filtration that you require for that drip emitter. This table kind of gives you a guide to that 10 times the orifice diameter. If you say had a micron of 105 for the emitter orifice size, you need 150 mesh equivalent filtration system. In British Columbia, we're always in that 120, 150, 180, 200. That's the range we're in. And of course, people will select their emitter quite often to have a larger orifice diameter so you can get by with a smaller filtration unit, less chance of plugging. When you do that, and have a higher orifice diameter, it means you also have a higher flow rate, which then translates into more zones and a larger controller and all of that, which is extra cost, but it might be of good value. Your run times go down because you're putting more water out, but that's done quite often to get away from this really fine filtration into maybe more like 150 mesh equivalent. The other thing you need to consider with screen filters is the percent open area, and they range. This is actually doesn't look very good. That says 31.4% to 30.7%. You can't see the dots too easy, but you need to know the percent open area to determine how much of a screen area you need. There's nothing wrong with having more filters, a higher screen capacity than what you really need. You never want to be less because you'll be fighting it all the time. You'll be cleaning the screens too often. So a higher screen area, this should really say minimum screen area. The formula gives you a calculation of what your flow rate is. You divide it by 448. The flow rate, the maximum velocity through your screen should not exceed 0.5 feet per second. That's very important. So 0.5 feet per second times the open area. And for example, if you're looking at a very small system of 28 gallons per minute per zone, and you had an open area of 0.336, this one here, 200 meshes per inch here, your screen area is about 0.37 square feet. So very small, not very big for a 28 gallons per minute, but obviously it increases as you go up. If it was me, I would probably put in 2 screen filters. And there's a good reason for this. If you're going to clean the screen, you have to have clean water to clean the screen to make sure no material gets in. So I want to take water that comes through one filter to clean the other filter. So I would always double it up, and I would probably have a higher filter capacity than what this is telling me, so that I don't have to clean the filters as often. It's a little bit extra cost, but over time, it's well worth it. So if we look at sand filters, you can see, you'll usually see something like this, where the sand filter, you don't see just one sand filter ever. Just like the screen filter, I have seen single screen filters, and in those cases, I think they're just putting it in case something breaks and they want the filter to capture things before it goes in the emitter, but they usually have really clean water. If you have dirty water, everything should be in tandem. And you'll notice here this is not in, this one on the right is not in British Columbia, this is in Washington State, very large system, and they've got 5 sand filters there. And there's a lot of things you need to consider about selecting a sand filter, which I'll go over. This is more our BC installations here, but you see you have 2 sand filters operating the system. So a couple things that you need to be wary of. The sand designates the filtration capacity. So if you're looking at number 16 silica sand, which is very common here in BC, it's got a mesh equivalent of 150 to 200 mesh. Number 11 crushed granite has also been used, 140 to 180 mesh. You cannot use swimming pool sand. People that have done that have caused a big problem in them operating their system. Doesn't do a good job. You need to get special sand designated for a sand filter for agriculture. So that's one of my recommendations for sure. And then pick the sand that you think is the equivalent mesh that you want to filter to. I noticed an error in this drawing after all these years of the manual. I never noticed this before, but I'll show it to you in a second. So in normal, a sand filter, the water flows through both sand filters, goes out through the system like so. Your design of this will depend on, obviously, how much water you want to force through the sand filter. And a recommended flow rate is 20 to 25 gallons per minute per square foot of area. Like I said before, always be installed in pairs or more than 2. When you go into filtration mode, what happens is the water comes in like it does here, goes through one sand filter, might still go out to the irrigation system, although you can have this automatically shut down as well. And then the water goes this way, and these arrows in the wrong direction. That's the arrow I found. The water would go this way, lift up the sand bed, flush the materials out the flush board. You need a certain amount of flow to be able to lift this sand bed. And there's a certain pressure differential upon which you should alter the pressure before and after the filters when you can tell they have to be cleaned. So it can all be set up automatically. You set the pressure differential at maybe 5 pounds or something like that. When that's reached, the system automatically can shut down the irrigation system for a minute, flush back one sand filter, turn it around a minute or two later, flush the other sand filter, and you're back in full operation. So the backflush flow rate is usually less than the filtration flow rate. 13 to 18 gallons per minute should say per square foot, depending on the type of sand you're using. So the problems you can run into is that you're setting your system up for 20 to 25 gallons per minute to come through, but you need a much more area to flush the other sand filter. And so that's why you might have to shut the system down. And this is important because people have made big mistakes. I'll show you a slide in a second about operating their sand filter. This particular table gives you a recommendation on the configuration and the square foot area. That's 52.5, not 525. The dots don't show up very well. So two 18-inch sand filters are 35 square feet. And if you had something a lot larger, two 30 inches would be 98 square feet. And then you go into combinations of 2 or 3 or 4 or 5 after that. So it gives you an idea about the size of sand filters you need to buy. So this is what I was alluding to a minute ago. I went on a trip to California one time in the Napa Valley. In the Napa Valley, they're irrigating their grape crops when they first plant them. Then as the plants grow up, they don't irrigate them as more. And we were there on a tour and this guy was saying, yeah, well, we irrigated for a few years and then we stopped irrigating because our drip system wasn't working anymore. And so we just abandoned it. So I was there with a friend of mine and we noticed they had these screens installed on every lateral as a backup procedure in case somebody malfunctioned the sand filter and kicked sand into the system. These screens would pick it up. A good idea. It also, if a line breaks, it would pick it up and you don't have to worry about your emitters getting plugged all the way down the stream. Well, we took apart one of these screens and it was totally plugged full of sand, as were all the other ones in the system, which is why the system wasn't running anymore. It had nothing to do with anything else other than that these screens were all plugged up and they never bothered to go and check on it. So sand filters, you need to be a little bit careful with every filtration system that you're not getting material back into the line after the sand filter. The secondary screen after the sand filter is a good idea just to pick that up, and then you can clean that every so often because you don't want to be going out and cleaning out every emitter or replacing your emitters. There's a lot of money invested there, so you want to make sure you're running the sand filter properly. So that leads us to,
Ted,
yes?
I would like to make you a question before moving forward.
Yeah.
We have one question say, how will you determine what size of organic material is in your water?
Well, you would take it to a lab. A lab can do those kind of tests for you, and they can tell you what the size of the particles are. You will probably always also have people in Nova Scotia that have run sand filters or run screen filters and are already doing something and they picked on the sides and it's working well. I'm sure, Michelle, if you know of people that are running it, you can find out what they're using if they've had problems. Yes, water quality can change from place to place, but that's kind of how we did it. We went and tested not every farm goes test the water, but what we did is we tested some of the irrigation districts at a lab and we found out what was in the water, changes all through the season, changes from year to year. But we got an idea about what the particle sizes were and what kind of filtration would be recommended on various districts. And now, of course, we're talking 35 years later, nobody really asked that question anymore. But if you don't know, you would go and get it done at the lab. And you might be able to do it yourself if you have some very fine mesh material and you know what it is, run the water through it and see if it picks anything up. And you will be able to determine that way as well. One of the things that we did do was we would put we'd collect water in a jar and let it settle and see if what's settled out as well. So it gives you a bit of idea of what's in the water. So chart kind of goes to that. It kind of tells you a little bit about what are the water quality guidelines for a drip system. And this is just based on experience, what we have here in BC and some other literature. So if, if it's like in these ranges here, you could probably have no problem running your drip system. If you're getting into this, it's a little bit more severe. You need definitely good filtration. And if you're here, I would consider not running a drip system. So those parameters are there. If you go get things tested, you can see where you lie. I'm not saying you cannot run a drip system here, but you really need to be on top of your filtration, chemical treatment, line flushing, and all those other kind of things. There's also a chemical rating for irrigation water, and you'll see that's in the book as well. So this chemical rating is really for two things. You want to be able to see if you have iron, high iron, whether you're going to need to treat with an acid to treat some of those kind of problems with your drip system. And usually, you know, if you have iron, if things are turning brown or if you're taking it out of a well and you can tell there's iron staining on the pipes and stuff, you've got a problem. And something that I would probably caution you in using a drip system if you have high iron levels, for sure. All of these other factors, pH, calcium, magnesium, sodium, potassium hydrochloride, they're all related to calcium carbonate precipitates. And we have that in BC. In some regions, if these values get high, you will get a precipitate forming at the emitter when it hits the air. And it's a little white, crusty material that forms over time that can plug up your emitter. Once your emitter is fully plugged, you're not going to be able to clean it very easily. Before it's plugged, you can treat it with an acid or maybe even chlorine, and you can help get the emitter cleared. So going into the system, if you test this at a lab and you find out what these levels are, you can see where you are, and you can say, I'm not going to have too much problem with this, or I'm going to have some problem. I better keep on top of it. So that leads us to adding chemicals to your drip system. So you need to chlorinate if you have a precipitate of iron or manganese oxides prior to filtration. So your chlorination unit needs to be before your filtration unit, because what the chlorination, or acid for that matter, acid dissolves things, but for chlorination, anything that causes the precipitate to precipitate out, you want it to be picked up in your filter and then be back flushed out. So if you're doing continuous chlorination, you're having to filter quite often. If you're just chlorinating the emitters and you're putting chlorine through the system to dissolve a chemical, that's not going to get filtered out in your filtration system. But the chlorination unit should always be installed before the filter unit. We also found that if you try to chlorinate above 40 milligrams per liter concentration, it really isn't going to be any more effective than 40 milligrams per liter or below. So that's about as high as I would recommend. And there's also issues about putting chlorine into the soil at very high doses. So 40 milligrams per liter is pretty safe. It's the highest recommended dose that I would go to. We do use acid to control precipitates. This can be added when necessary too. And so if you think your emitter system is plugging up a little bit, you can add an acid for a number of hours to dissolve that, run your system, dissolve it. You can also, we had one fellow do this in BC where he had high iron. Every year he took all his lateral lines and he put them in an acid bath at the end of the season for a number of hours. He just cycled them through and then they were all kind of clean and used them again next year. A huge task just to be able to run a drip system. And he knew he had iron going in because all the tree trunks were stained brown from iron from all the people that were using sprinklers. So they had a real problem with water quality from a well in that particular location. And I mentioned that the chemical injector should be installed prior to the filtration system. So how do you know if your system is actually performing the way it should? And the way to do that is to do an emitter flow check. It does two things, actually. You can check the emitter flow rate when it's new, and you can take a number of emitters or do, if you have a line source system, you might want to put it over a trough, run a section of it with so many emission points, collect it over a certain time period and say, I'm getting this much water. You do it again at the end of the season and see if it's the same. If it's gone down, you might think, oh, I got to give it a bit of a treatment with chlorine or something to clean the lines. And then you can test it again to see if it's come up or not. You should also line flush. Precipitates and algaes and all that will always collect near the end of the line. So line flushing at least once a season is a good idea at the end of the year. If you have individual emitters, you can collect them just in a bucket like this and see if they're going down. So yes, it could be determined, you can determine if your flow rate is staying the same, which is important. But you can also use this methodology to see if you have good uniformity. Test the emitters at the beginning close to the shutoff valve, the automatic valve that runs your system, and then go to the furthest point and test the emitters there. Are they providing the same amount of water? They should be, if they're pressure and compensating for sure. And so you can see if you actually do have good uniformity throughout the system. And farmers don't usually do this because they don't get into the weeds, I'll use that word, of checking things out to see if the water's still dripping out, it's fine. But uniformity is important because if one plant's getting more water than another, it would go to say that one of those plants wouldn't be doing as well. So checking the uniformity, don't have to do it a lot, but just to see where your things are at is a good idea. And if it's not uniform when it's new, then it goes back to the design of the system. Something wasn't set up right. Okay, I'll stop at this point. One of the things that's important before we talk about scheduling is that there's really no point to schedule a system that isn't being run properly. If your system is not run properly, then scheduling isn't really going to help you. What are you scheduling to, the high or the low? So you really want to make sure that when you get into some kind of scheduling, that you have some idea of what's going on in your system, and that for the most part, you've got pretty good uniformity. So that's a key point. And if you are comfortable that your system is running pretty well, we can get into scheduling. So as I mentioned, we run our drip systems to match the peak time of the year. This blue line is the crop water demand. It goes up during the peak of the season, then goes back down again. Our drip system is run to closely match that peak flow rate required by the crop demand by the system. And if you look at your average irrigation flow rate over the season, of course, it's much less. I put this in there because water license people average things, and that's not how we run irrigation systems. We run them to the peak. Yes, we need to stay, the average over the year was okay, but we run them to the peak of the year. So what that means is that, and this is actual data out of the Southeast Colonial Irrigation District, it is a long time ago, back in the 90s. And so this is the water requirement that we were actually calculating at the time using climate data and other things about what the crop demand should be. And this is actually what the producers were running their systems at. So what's under this line is water that's been applied that doesn't need to be applied. Now this would be an extreme situation. We picked a person that was obviously not scheduling at all, just running the system pretty well all the time, and basically using a lot of water that it didn't have to use. And when we go back to our water requirement that I gave at the beginning here for those two examples, we were around 7,000 cubic meters. If you were doing something like this, you would never be within the 7,000 cubic meters. You have to schedule your system to kind of follow the crop water demand, because that's how that calculation is made. It's about the crop water demand. So there's a number of irrigation scheduling methods. I'm going to talk about soil monitoring, the soil method, and of course there's the climatic method. So for soil moisture monitoring, there's a lot of new technology. I'll talk to you a little bit about some of the new technology we tested a little while ago, but some of the staples are tensiometers, which the question was about, electrical resistant blocks or watermarks, and there's also TDR technology. This Tensiometers and watermarks. Watermarks are probably the cheapest alternative because they don't cost that much. You do have to install them on a piece of pipe and put them in the ground. You do have to buy a meter, but you can buy an awful lot of these, leave them in the ground, and the meter you can just take from one place to another. So that's probably the cheapest method to go if you are using a lot of them. Tensiometers are not that expensive. They're a little bit more expensive, but you can get the reading right off the unit. And TDR technology, time domain reflectometry, is quite expensive. The meter is quite expensive. The unit you stick in the ground, they're not that cheap. They are used by people with high value crops, and they will hire people to come in and give them results of this. This is an older version of it, but there's newer technology. So things are changing all the time on soil moisture monitoring devices. So let's look at a tensiometer. I'll start with that one. So it has a reservoir at the top. This reservoir is you fill it up with water and then you clamp this thing down. When you fill it up with water, there's also a device, sort of a suction cup that you prime it, pulls all the air out of this ceramic tube. So it creates a vacuum in here. This is filled with water when you start, and then you pull all the air out, and then you put the cap down to seal this off so that this cannot have any air go into it. This can be filled up with water so that if you need to add water to this device later, you don't have to carry water with you. You just open the cap, let the water drain in, reprime it, and put the cap back down. The reading come on the gauge. And when you look at the gauge here, you can see these different numbers in centibars, 10, 20, 30, 40, 50. I remember giving this technology to a farmer in the Peace River, and he was trying to get this needle to move up by applying more and more water. And he says the unit doesn't work because he was thinking that this was percent soil moisture and he couldn't get it to go above 0. And when we were there and we dug down into the soil, it was a clay soil. We only had to dig down 6 inches and we hit water. The whole filled up with water. So you never even tested that. And so the moral of this story is the lower the reading is, the more water you have in the soil. The higher the reading is, the soil starts to dry out. We always, if you have a deep-rooted crop, you might want to have 2 tensiometers in the same location close to each other. It's going to give you the reading close to the surface, and it's going to give you the reading down below. And so your zone of moisture control then is in between. You can see what's going on. You might decide that there's lots of water down deep, there's not much water near the surface. We'll give it a small irrigation to bring this level back up again. So you can make some decisions on your application by having 2 in place. Watermarks, as I mentioned, the watermark is actually this little device here with a electrical lead that goes up this tube and then gets tied to these 2 little bolts in the top of the tube that you clamp your reader on. So they get installed just like a tensiometer. You put a hole in the ground, you slide these down, make sure you have good contact at this point. They also just give you the reading at this point, and you go to the meter and get the reading. So what are the differences between tensiometers and watermarks? Tensiometers can only read up to about 60 centibars. They do not work well in clay if you want to get a reading above that. They'll crash and you'll have to go reprime them and you will never get a good reading. Watermarks can read up to 200 centibars. So if you're in clay and you need to be able to get that soil moisture dried out to a point of about 80, 90, 100 centibars, you're going to have to use a watermark. Can't use a tensiometer. Tensiometers need to be removed in the winter because there's water in the column and they'll freeze and break. And you're going to have to constantly monitor a tensiometer. Watermarks, you can put them in the ground and you can just leave them there and you don't have to do anything and you just go back and read them the following year, providing that you've installed them correctly. So there's a chart in your manual that converts the readings of actual soil moisture to the centibars on the tensiometer or the watermark. And that changes for different soil types. So normally with sprinkler irrigation, we're looking for maybe 50% depletion when we know that it's hard for the crop to take the water out again, and we're going to want to irrigate. So we'd be using the 50 centibar line to determine what the reading of the tensiometer would be. For drip systems, we want to be higher than that. We never want to be at 50%. We want to keep the soil moisture at a higher level, probably at about a 20%, 10 to 20% depletion. You can choose that. It'll be in that range. You don't want to be saturated, so you want it to be down a little bit. And so I would recommend a range of 10 to 20. Question about whether, you know, that's at bloom or at time of harvest or whatever. I'm not a crop person, so somebody, maybe Michelle or others, can give some advice on that. But my recommendation is you would be in this range. So if we take a look at an example here, if I'm going to use the 20% depletion, then I'm going to go down and say I'm running it on a fine sandy loam soil, and I went across. It seems I have to be around 15 centibars. So I go to my gauge on my tensiometer, and if I'm reading around 15 centibars, I'm right where I want to be. If this thing is read down to 0, that means it's crashed. You have to reprime it. If I was at the 20% depletion and I wanted to go look at clay, though, I'm going to have to be at 70 centibars. And this tensiometer may not read that high. In fact, I've never seen any read that high. If you're using it for a sprinkler system and you want to go down to 50% depletion, you're way down here and you're at about 100, 200 centibars. Watermark can do that, but a tensiometer will never be able to do that. And same thing for in a loam soil. So tensiometers are good in this range in here. If you're wanting to get to, you know, 60, 50 centibars, you can get a reading, but they're limited. And so you should recognize that. There's also lots of other types of sensors that we're getting into. Technologies that expanded beyond strictly soil sensors. We have plant monitoring sensors that tells us how well the plant's doing. They're attached to the trunks or leaves and fruit. They're all being used now on different variety of crops. This technology is moving very, very quickly. Certainly something you can try if you have somebody local that's promoting one of these as a demonstration project. There are problems though, you know, you don't know if you're doing a leaf, for example, is that leaf representative of the whole tree? What part of the tree do you take the leaf from? Trunk sensors may be a bit better. And I've come across this technology and I've seen that it works, but I've also seen problems with it. I was in Israel where they were monitoring a tree fruit crop with a sensor on the leaf. And while we were there, the system turned on because the leaf would wilted a little bit. It was losing the tension of the leaf, I guess. And it ran for a few minutes and it turned off again. And so it did that all day long. So very sophisticated technology that they were trying. I don't think they were using it commercially yet, but they were certainly trying it. We ran a project in BC on automated soil moisture sensors. And we installed these in nurseries in various locations of the province. And I don't know if I have another slide of it or not. Yes, I do. So we installed 3 or 4 soil moisture sensors in each location. Then we averaged the value of those sensors to determine whether irrigation should go on or not. And so what the sensor did, it overrode the controller. It would send a signal saying there's enough moisture, skip this irrigation. So you'd set the irrigation and then the sensor would tell you if you need it or not. You might wait a few hours and then the sensor would say, yes, you can irrigate now. And then the irrigation system would come on. And it would be a sprinkler system in this case. So it seemed to work very good. We saved water. Growers liked it. But the company that developed this technology never went to commercial production because we did have problems with it. And we found things that, like everything, it was a demonstration project. So we were on top of it all the time, but not something that a grower was likely going to do. So they realized that there's some problems with this technology they had to fix. It was wireless. There was problems with sending it too far. Buildings got in the way. So we had to pick locations that had direct line of sight to a receiver. Lots of other little things. So to my knowledge, I don't know if this thing has actually been developed or not, but there would be others around that would probably be quite similar. Okay, I'll stop here for a sec. Any questions on soil moisture monitoring?
Till now, we don't have any question, but we have a comment that I can read you. Okay,
Sure.
in the chat. Somebody wrote, I found that getting the watermarks installed correctly is tricky and become inaccurate if not done correctly. So he was asking a question to the public in general. Has anyone else had this experience? So I don't know if you can comment a little bit.
I can talk a little bit about that. When we did a demonstration project, when I showed you that data from Southeast Kelowna about the beginning of the year and how they were over applying, we had a project going in that time, and we installed tensiometers on 10 sites and watermarks. And we provided the data to the growers about whether they should irrigate or not. We had a student that went around, read them, told the grower, you don't have to irrigate right now. You can wait a few days or whatever. It was very good for the growers that followed it. And one grower was very close to what we calculated his use should be. He was almost bang on. But what we found was that we also had problems installing the tensiometers. You put them in and they often crash because they weren't reading properly. Same thing with the watermarks. So you really need to have good contact with the soil. So we had a rod that was the same diameter of the watermark of the tensiometer. We pounded that into the ground. We made a soil slurry, made it wet, poured that into the hole, and then pushed the unit in until, and we also knew exactly how deep it was so that we made sure that the bottom, the tip of the watermark of the tensiometer actually reached the bottom of the hole. And then it would, within minutes, it would start to read. And then we knew we installed it properly. So I don't know if that's the problem experience there, but they can be finicky. You have to make sure, you have to put a soil slurry in. And a clay soil slurry would be good, not, just something that would go around the unit, make contact, good contact with the soil. That's very important.
And I have another question here, Ted.
Yeah.
Or a comment, I don't know. Just a note on the watermark sensors. The company also has a data collector which will remotely collect the data versus manually collecting.
Yeah, this technology is all coming along. You can also get tensiometers that override your irrigation system, just like this sensor we're showing here. So the technology's moved a long ways along from when I was playing with it. So that's why I'm kind of giving you guys general guidelines, because there's probably better technology out there. I'm sure barometers are better. Watermarks may be better. There's other technology out there. People will have played with these that can give better advice than I can. So yes, I'm pretty sure that all of this stuff is going electronic and will work that way.
And I have two more questions.
Okay.
So sorry.
That's
What's
okay.
a good way to measure moisture when growing in substrate?
Well, that's what we're doing here. If you look at this picture, this is not a soil. This is a mixture of wood waste and other material that they plant the plants into the pot in. And we installed these sensors right into that pot, into that root ball. So I don't, and growers do the same thing when they're growing in rock wool or in greenhouses and that. So the challenge now is what is the moisture level that I want to look at in there? What is the moisture holding capacity? And I think I can't answer that question. You need to, I think the good growers, what they do is they experiment a little bit. They put it in, they get the reading, they say, okay, I think I'm too wet, I'm going to dry it out a bit, or I'm too dry, I'm going to increase it a bit. They do a little bit of playing themselves, because in the end, their substrate isn't the same as anybody else's substrate either. So they're continually fiddling around with it and pretty soon land on what they're going to do. And the plant seems to grow fine, so that's what they're going to do, right? What was the other question?
And the last one is, would you use a clay slurry even if your soil is a different soil type, for example, sandy loam?
Yeah, good question. We did, because we're not putting a lot of it in there, just a little bit. If you can make a slurry out of the sandy loam, that might be better. We had sort of made up the slurry. She went around and it was pre-made, and so she poured it in each hole, and it seemed to work fine. But I know what you're saying. Wouldn't that change things? But it just really, it's like the ceramic tip. It's not part of the soil. It's just letting water through and into it's pulling water out of the tensiometer is what it's doing. So the little bit of clay that you've added isn't going to pull a lot more water out. It's going to be the root zone around that that's drying out. That's going to get the water to move from the tensiometer into the soil, which creates the vacuum, right? So I'm not so sure it would make a big difference, but if you're concerned about that, if you can make a slurry out of the soil type that you have, that's probably a little bit better. We were going from farm to farm to farm, and so she didn't want to make up slurries everywhere, so she made up a slurry that she could just take along. Okay?
Yep, thank you.
Yeah. Okay, so now let's move over to climate monitoring. We talked a little bit about this at the last session about determining climate data that you can use to determine how much water you need, peak flow rates and all of that. But you can also use that climate data to schedule your irrigation system. And it's based on how much water is my plant taking every day and what's being evaporated from the plants and the soil surface. You got to be careful here because you need to know something about the crop coefficient for your crop. And there is some guidance on crop coefficients in the manual, but different plant species can have quite a big difference in the rate of transpiration. So if you go to the extreme and you're looking at a cactus plant in the desert, or you happen to have an apple tree growing close by that was being irrigated, they obviously have two different water requirements, and it's about the crop coefficient and how that plant uses the water. So we need to consider crop coefficients when we're using climate data to determine a schedule. So when we're talking about climate monitoring, we have a number of different devices. We have anemometers. I like the anemometer because I don't know if they're still sold. They came out of Fort Collins, Colorado at one time. You install them, you fill them up with water, put the little cap on there. It will actually, you can actually read it on the side. Right here, there's a scale. You can read how much evapotranspiration has happened, but it also records electronically. So you can have this data sent to your computer and it'll give you the ET value of the day. Class A pans don't really use them. Research stations use them, probably still have them because research was based on that years ago before weather stations really came in. So they still may have them, but we have used wash tubs to mimic a Class A pan. And some people did that. They put a wash tub out there, put a screen over it so animals wouldn't drink out of it, and just recorded the level of the water in the wash tub as an indication of evaporation. When we came along with Farm West and we had weather stations, this kind of all dropped by the side, as did this a bit, because now you can go to your computer and you can pull the data right off your computer about what the weather station provided you. Now, you should also, if you're doing some other method, you need to know what about the effective rainfall. So you need a rain gauge as well. If you're putting in a weather station, you need to know how much water came from the sky so you don't have to irrigate that amount. And one of the things that Farm West does is that we eliminate any precipitation under 5 millimeters. So we only count the precipitation over 5 millimeters because the first little skiff of rainfall that falls doesn't really enter the soil usually, and it evaporates off and it isn't giving the plant any effective water. And then what Farm West does, it only takes 75% of the values. We eliminate 25% over 5 millimeters. So if it rained 10 millimeters, we would only give it credit for 7.5. That's just based on a bunch of literature, and you can run into trouble when you do this, because if you take the Fraser Valley, for example, where I live, you might get 10 days in a row with 5 or 7 millimeters. So over 10 days, you've had 50 millimeters been applied, and you've thrown all of it out because it was under 5 millimeters, most of it. And then I can see that we're running into trouble. So you have to be cautious about that when you're looking at climate and moisture deficits calculated even on the Farm West site. And so a soil moisture monitoring device to see if the soil moisture is going up or down would also be useful. But for the most part, if it isn't raining at all, then the climate moisture deficit is a good way to go. So the Farm West website includes 4 stations in Nova Scotia that I mentioned before. And it is tied into this calculator that is shown down here. And at the end of this presentation, I'm going to take you to the calculator and I'll show you how it works. So when you're doing climatic irrigation scheduling, you're using a climate station data usually, to track the actual evapotranspiration or climate moisture deficit. Remember that the irrigation systems are designed using the peak ET. So when the actual ET consumes all of the water stored in the soil, if you're doing this water checkbook balance, it would be time to irrigate. So let's just look at a simple schedule. Let's say my ET is 4 millimeters. And I've determined through all my calculations that my operating time is 150 minutes of operating time. And I've monitored the soil moisture, and that seems to be a really good way to go. Once you've established that, you can just go back to your, wherever you're getting your ET from, and do a quick calculation. So now it's 3 millimeters. Well, 3 millimeters is 75% of 4 millimeters, so it's 112 minutes of operating time instead of 150. So what you can do is you can kind of look at the week, see what the ET is coming up, because Farm West also forecasts ET based on Environment Canada stations. You can say, well, it looks like the ET over the next 4 days is going to be 4 millimeters. So I'm going to set my operating time on my controller to, in this case, 150 minutes, and just run it like that. And then next year you can make a new evaluation about how long you have to run. Remember, you're always running your drip system at about 80% of peak soil water. So even if you're off a little bit, there's water in the soil that the plant will rely on. And you're also not using up 24 hours a day. So if you fall behind, you can always add more to get caught up a little bit if it seems like it's drying out a little bit. But this is a good way to not over apply. You cannot take water out of the soil. You can always add more water in. So if you're scheduling and you've decided you've put too much water on, and then you get rainfall after that, you're just getting in a situation where you're stuck with, you know, too high a soil moisture, and that may not be good for your crop either. So I'm going to take you to this irrigation scheduling calculator. I'm going to have to just see what the next slide is. So this agriculture scheduling calculator was developed by the Irrigation Industry Association of British Columbia. It works for any crop. There is an agriculture calculator that I'm showing you the icon here, but there's also a landscape calculator, so you can use it for any kind of crop, any kind of irrigation system. It sits on the IBC website at www.irrigationbc.com. That's where you go to find it. So I'm going to go, I think I have to stop share. I could click on this, and I wonder if it would bring me in automatically here to this thing. Let me see. May not happen. Can you guys see the screen?
We're still seeing your presentation.
Yes, see, that's what I thought. So I'll stop share, and then I'll share screen with this calculator.
Just to let you know, Ted, after the last questions, somebody wrote that Ocean Spray in BC has done a lot of testings on sensors, and it's leaving a link from BC Cranberries.
Oh, good to know. Can you see the screen now, Francisco?
Yep.
Okay, so I'm on the IBC website. I may have to stop sharing again. I'll just see. On the bottom of their website right here is the calculators. This one's got the landscape calculator. You push the arrow over to the agriculture calculator, click on that. Can you guys see the calculator?
Yes.
Good. All right. You need to log in. This is because you're going to be putting in your information. So if this is the first visit to the calculator, you would click here, develop an account. Once you have your account, you don't have to do that anymore. You just log in here with a password. You better remember it. Otherwise, you'll have to kind of get a new password or set up a new account, which is a pain. So, and you can switch over to the landscape calculator here too. We won't bother with that. The data comes from farmwest.com. It feeds into this calculator. So I'm going to log in on my account. This is just something that everybody has to agree that you can't sue us if you're using this and something goes wrong. It's just a disclaimer. And so now I'm in the calculator, and just a second, I got to move this over. So I have already set up Kentville as an example, and I'm going to do a new system. I did one on blueberries already, but I'm going to do a new system, and I'll call it Blueberries 2. So it clears the screen here. My video keeps getting in the way here. I'll put it on here. Okay, so I'm in a thing called Blueberries 2. I haven't added any information in, so let's do that. I'm growing blueberries, obviously, so I'll click in that. And you'll notice immediately the calculator provides you with the information, the depth of the roots, availability coefficients, and climate coefficients by the month. You can change these, but these are the ones we have in a standard, and you can be changed if you like. So pretty simple. All you got to do is click on the crop. The next step, you'll see there's 4 steps here. I've done the crop, there's soil, irrigation, and scheduling. So my next step is to go and look at the soil. So I've got to add a soil layer. I'm going to use the same example that we did here. So it was a clay loam soil, I believe. I've got to make the depth of that soil to be at least as deep as my plant, otherwise it won't like it. If I had made that 12 inches, it would have said you need to add more soil because you said there was a 2-foot rooting depth and you only have 12 inches of soil, say. So I added enough here just to keep it simple. It immediately starts to populate the total soil storage, the maximum application rate, soil water deficit, and our initial soil moisture, which we're saying is 25%, but you can change that value if you want. This is at the start of the irrigation season. So, so I've added my soil stuff in. It does everything else for you. So now I'm going to go to my irrigation design. Oh, wait a second. I'm going to, I'll tell you what's happened here. And this is really important because I made the same mistake here. I'm going to go back here and just show you what's happening here. When I go, I'm going to do this really quickly again. I'll say this is really important because a lot of people have this mistake and they don't know why, and I just did the same thing. So I'll add my soil layer back in. And now I go to my irrigation system, and what's prompting me is a pivot. And it's prompting me that because I didn't go in when I set up this scenario, I didn't pick the right kind of irrigation system. And I have to say that I'm using a drip system so that it loads up the drip system sheet. And I didn't do that. And so people say, why? And if they don't do it, you'll get the same thing. So make sure at the very beginning that you do that. So I'm going to go back and I'm going to use this other blueberry scenario because I'm really entering the same information that I did before. So we're back to our blueberries here. Our soils is 24 inches. And now I get the form for my drip system, which is what I wanted. So 2 emitters per plant. The flow rate per emitter is half a gallon per hour. It's asking you when you want to run it. It doesn't, you need to put something in here. I'll say every day, and I'm going to say my system runtime because I've calculated, I'll say around 5 hours. This doesn't matter too much either, but it's asking you to put that in, so that's fine. It gives me my application efficiency and emission uniformity. You can change that if you want. And it tells me right away that the gross water supply per plant is 5 gallons per irrigation, which is what we want. So we have all the information we need for crop soil irrigation. So now we can schedule. So you click on the scheduling tab. We're in Nova Scotia, we're in Kentville. I'm picking a date here of July 21st, 2020, and I'm picking an end date here of July 24th, 2020. You can pick whatever range you want. Once you've done that, you want to load and update your graphs. And it'll do that, or it should. It's working properly. Which it seems like it's, there we go. So it's giving me a runtime here of about 2 hours based on the ET of that time. So it's scheduling your irrigation. If you pick a different time, probably because we had rainfall in here as well, but if you pick a different time in the year, it'll go up. And so it'll change. So we're around 1.5 hours, 2 hours, whatever. At this point in time, we said we needed to run 5 hours. If your ET was higher and you had no rainfall, you may get a higher run time. It also tells you the net of water applied per plant, your plant water requirement in gallons. It's all in here, what's happening, and what the future prediction is going to be. So the calculator really does what we did manually. And once you put in your parameters, if I go back to the main tab here, there's a way of browsing that, just a second. Go back to the browser. Once you put in your scenarios in here, you don't have to do any of that work anymore. You can go directly to the scheduling tab, pull in your data for the time you want, and it'll give you an answer. So, you know, I've done in here things for, I'll just show you a little bit. I know that this is not something, if we're doing a wheel move system on alfalfa, and I completed those worksheets. I just want to, I'm just going to go directly to the irrigation system scheduling. This is, I'll just load up the graphs that we have. You'll see a whole different format that comes up. So you can use this not only for a drip system, you can use it for any type of sprinkler system too, or pivot. And what this is telling me that you have to put in the tool, when was the first day of your irrigation? And in this case, it was on August the 2nd. And then you also have to say how many days between your next irrigation. And then the tool tells you how much water is left remaining in the soil. So you can see here that after, in this case, 5 days, there's still water left. And if this goes below, it'll turn orange, meaning now it's time to irrigate. So when you finish your irrigation, you kind of wait until this is turning orange, and it tells, okay, start my sprinkler system, and then go across your field again. With the drip system, it's giving you an hourly, daily application time. So, so with that, that's kind of what the end of what I was going to talk to you guys about. I don't know if there's any other question. I can answer any other questions that you have. I don't think I have anything else to present.
Yeah, we have another question, and it's similar to what you have done right now. It's, could you do a drip irrigation example where it's not based on water requirement per plant? Example, using drip tape on corn or wheat?
Well, I can try that. Go back to my browser. We don't use drip on wheat very often, so we may not even have that in the calculator, but let me just see. It may not be there. So we're going to create a new field. We don't want to be in Alberta. We want to be in British Columbia. It's going to be hard for me to do because plant spacing and row spacing and all that we would have to make up, but I'm not so sure I could be successful on that. What would be we haven't used drip on wheat, so I don't think this calculator will do that, because we don't have the proper, I mean, I can generate something, but it will be a guess by golly, and it'll also generate, I have to make up a crop coefficient. I mean, I can try it, I guess. Let me try it and see if I can make it work. Oops.
Well, we have a follow-up of that question, Ted. It's, for example, a surface irrigation in wheat or corn, if that's possible.
Say that again.
Follow up to question, subsurface irrigation in wheat or corn?
Sir, you're talking about flood irrigation?
I suppose it's the follow-up of the question that I already did.
I'm not sure what you're asking though. I'm not sure what's being asked. This doesn't do flood irrigation either. It's one system that we don't do. So notice here, I have to pick the type of irrigation system type to make sure that the right things will be entered. And I got to also say something about the field. So I'll just make something up here. Okay, I don't know if wheat is even on here. And it won't be because we've never done it. So
okay.
I'll take corn.
The subsurface irrigation means like lines are placed in soil below plow line.
Okay, it's called, you're talking about subsurface drip?
Yeah, appears only surface irrigation.
We do subsurface drip. So where we put the drip system underground, and that's done quite often. And we, you know, you might be down 3 or 4 inches. That's mainly to keep it out of the way of people tripping over and things like that. But I'm not quite sure what the question is.
I think he was saying an alternative example that you could show could be the subsurface irrigation.
Subsurface drip. It wouldn't change much from what we just did there. The only thing that would change would be your efficiency. So everything else would run through the same. So, so do you guys want? I'm not quite sure. Do you want me to continue on this example or go back
as you wish? If you want to continue,
well, let's just see what happens now that we've started this thing here. So let's see if we can even get an answer. I'll call it something like sandy loam. You can also add more than one layer, which I had here. So there you go. So you can stack your soil layers. If you have a foot of sand or a foot of clay, you can put that in here and stack it. So we're having a linear tape system here. I'm just making these numbers up. We'll see what happens when we calculate this. Having a problem. We're having a problem with this because it doesn't show us the length of run to get total gallons per minute. So
I have other questions.
Yeah.
If you want, we can continue moving forward. How does plastic mulch over the drip line affect calculations?
It will improve your efficiency. And so your efficiency might go from 90% to 95%. It doesn't do anything with moving the water laterally or anything else. We use a lot of mulch, plastic mulch and other mulches, and so your efficiency just improves. I'm not going to be able to do this example because we're doing something that's outside what the calculator can do. So we won't do that. I can just see there's all kinds of things coming up here that isn't quite right. So
okay. Another question is organic peroxide like Sanidate good for line flushing?
When I line flush, I didn't add anything. I just always opened up the line at the end, and they should always be able to be opened up, and just let it run until it ran clear. It would run dirty for a little while, and when it run clear, then the line was flush. You're not really flush when you're putting a chemical through. It might help, and I'm not going to give any advice as to which chemical to do that. But when I talk about line flushing, I'm just talking about open up the lines and let the line run clear, because your line, all the material is going to build up at the end of your line. That's where it's going to start plugging the emitters. So, it'll start to run clear in a very short period of time and it'll look black when you open up the line to let it flush. Whether anything in the line assists in that, if you add a chemical, I'm not so sure.
Okay. Other question is, what is your opinion of the two probe resistant or capacitance type soil moisture probes?
Are you talking about, so the capacity, isn't that what a watermark is?
I'm not sure.
I'm not sure about that. You know what? I can't answer that question. It has been a long time since I've been in the field with this stuff. So if you had asked 20 years ago, I would probably have a better idea. But, the ones that I'm familiar with are the TDR, the Grow Point, the one that explained that we used in the different nurseries, tensiometers and watermarks. Those are the ones I have experience with. I haven't really used a lot of other types of technology, and that doesn't mean that they're not good. They could be very good, but I really can't answer that question.
Okay. Well, this is coming from the previous questions about the exercise. Southern irrigation in British Columbia, Alberta is starting to market this tech to growers. I think it's the subsurface line, and it's also becoming very popular with broad acre crops in the US and Ontario.
You're talking about subsurface. You're talking about subsurface irrigation.
Yeah, I have the impression is that.
Yeah. And Southern Irrigation, by the way, is a very good company. They're very proactive. Their people are certified designers. And like I said, a lot of companies are going to subsurface on raspberries and crops like that. They're burying the product under the ground. And nothing wrong with that. The only problem with that I see is that you have to have good confidence in your filtration system that the system is still running. Because if an emitter clogs up, it's not as easy to determine that emitter is plugged as if it's sitting above the surface.
Okay. We have a couple of questions, Ted, by the way, 5. Growing strawberries in a raised bed on ground substrate based system on landscape ground cover. How can I schedule irrigation with a system such as this?
Well, we grow our strawberries in a raised bed with plastic mulch, and the drip line goes underneath it. So can you repeat the last part of that question?
I will read completely. Growing strawberries in a raised bed on ground substrate based system on landscape ground cover. How can I schedule irrigation with a system such as this?
We talked about substrates. Like, we grow in greenhouses and substrates, and we have devices that measure the soil moisture in there, and then the grower determines what level he wants to keep it at, and he runs. So I don't see this being any different. You could either go the climate method if you had an idea that your run time was right and you saw how the climate was changing, you would do that. Obviously, that doesn't work in a greenhouse because you're under glass. But if you're outdoors and you're growing strawberries in a substrate, you would put your soil moisture sensor into that substrate and determine what it's reading and what level you want the moisture at. You can also use the hand feel method, right? You can squeeze the substrates and see how much water is in there. And so you would get good. And I've always told people this: if you start playing around with this stuff and trying different things, you will become the expert. There's nobody else that's going to go out there and say you should do this or should do that, because you've actually played with it. I haven't. I haven't played with strawberries in a substrate. So I don't know what substrate, what the holding capacity of it is, how you're growing your strawberries, how close together they are. You'd have to work all those things out.
Okay. Unrelated to AgriCalculator, Would you know if subsurface drip is any success / benefit for apple orchards, since drip is closer to root system? Do you think it is more beneficial over trickle irrigation?
I consider drip trickle to be the same. We calculate it the same. It's just the type of emitter that you're using. And some farms don't like drip irrigation because they want to see an emitter that throws the water out, so you have a larger wetted pattern. I think in our previous seminar in December, we talked a little bit about that, about you need to irrigate enough of the rooting area. It doesn't matter how far the drip system is above the plant or above the ground. It drips down, it hits the ground, and it will move laterally a certain distance. And you just want to make sure that you have enough emitters on that plant to irrigate a sufficient volume of the root zone. If you're using a spray emitter, you have a better chance of that. And so some people have gone that route. Some people now, what's very popular is micro sprinklers. Micro sprinklers are not designed like a drip system. They're designed like a sprinkler system because you're throwing the water over the entire area. And so you need to account for that. Whereas the spray emitter is still applying water only to the panel or where the roots are and not to the middle of the panel. At least it shouldn't be. So different ways of looking at it, but it's your preference. On a very, very sandy soil, very sandy, where you cannot get much lateral water movement, I would be using a spray emitter system. If your water is a little bit heavier, sandy loams and that, a drip system should work fine.
Okay. Any tips for winterizing a system at the end of the season?
Yeah, you get a compressor, and there should be people in this business that hook up to your system and blow out the system with air. That would be my recommendation, because the drip lines will probably survive the winter and freeze ups because they are made out of a softer plastic and can expand and all that. If your header lines and everything that's made out of PVC or other products will break if it freezes, so they have to be cleaned out. If they're all on grade and you have drains that you can drain them and you're confident of that, that can be done. But the safest route by far is to hire somebody to blow it out with air.
Thank you. Two more, we are the two last. How to add Nova Scotia weather stations, for example, Pictou County?
Right now, I think we've got the Environment Canada stations. If you wanted another station in Nova Scotia to be hooked up to Farm West, and so it would work with this calculator, and that's the only place you can put it to work with the calculator. You can't go into any other system to have this calculator work. It needs to be added to Farm West. Really what we would like is a network. Like if Nova Scotia, because you're far away, it's better to have a network where you say, we've got 3 or 4 stations, Nova Scotia will run them, we'll set it all up, and then we just pull the data in from those stations, all 4 of them, or whatever the number is, into Farm West. And but you're taking responsibility for your stations. So that can be done. We do that a lot now. We've got a network in the Okanagan that somebody else looks after. We pull the data in. We've got Metro Vancouver's network, and we pull their data in. But they're looking after the network, and we go into their website to pull the data in. That's by far the easiest way to go. Farmers in BC, we do allow farmers in BC to get their own weather station, and then they have to get a device that sends the data to a company that will collect the data on their behalf, and then we pull it from that company. We don't pull from an individual station. It's too hard for us to maintain and manage all of that. So we have 20 farmers that have their own station that send the data into the ROM network in Kelowna, and then we pull it from there into Farm West.
Okay, and the last question, where do you buy Watermark?
You should be able to buy them from your irrigation company. I think the company that sells aerometers also sells watermarks. If they're selling scheduling or soil moisture monitoring equipment, they should be able to track it down and buy it. I'm sure you can look online as well. We bought them from the same company that sold us the tensiometers.
Perfect. Thank you very much, Ted. These are all the questions.
Okay.
Excellent. Thank you, Ted. A round of applause. Thanks so much for leading part 1 and part 2 sessions. I know I learned a lot, and I hope that our participants did too. So thank you very much.
You're welcome.
And I also just want to share my presentation here quickly, just to show you all that that we do have an upcoming session in this Getting Into the Weeds series. So the next one is February the 8th from 2 to 3:30 p.m. Atlantic time. And that's going to be on pivot and guns irrigation system management. Also, if you did attend this session, please remember to fill out the survey. That's going to come to your email inboxes pretty soon. And we are going to be doing a draw every couple of sessions here for anybody who fills out the survey. And in that draw, you could win one of the BC irrigation manuals. So we hope to be able to give that prize to one of you. Also, here's the contact information for Francisco and myself. So please feel free to reach out anytime if you have any questions. And thanks again, Ted.
You're welcome.
So that concludes our webinar today. Thanks, everyone.
All right. Bye-bye.
Yeah, thank you, Ted.